quantum solution will remain positive as well. So this should be working out as long as the only difference is we might have just a different time step restriction. And the way we're really going to do this is if we're going to look at this Shu-Oshia form of our Roman method. So if we can, we call this an S-stage method because we say S stages, but really it takes S function evaluations of U in this form. And as you see really right here, we kind of have a forward this time step right here. We have U plus delta T F of U. That's really what it is. So we're going to rewrite this a little bit to make it clearly look like a convex combination. If we factor out this alpha, we really just have this weight times a forward order time step with a modified time, a forward order method with a modified time step. And this will ensure positivity for U1 as long as you follow the certain time step, and it'll preserve this positivity in all the internal stages. This will be true under certain requirements. First off, you have to make sure the sum of 1 minus the summation of all your alphas are less a positive. So basically, this multiplication here, that must be a positive coefficient. These alphas must be positive, and this ratio of beta over alpha must also be positive. So since before, all your alphas and betas are positive, and your sum of alphas must be less than 1. All right, so that's the first one, the non-negative coefficients, and that kind of makes sense. The next thing is, beta ij has to equal 0 whenever alpha ij equals 0. That's clear right here, because remember we factored out this alpha. So if alpha is 0, we kind of have to divide by 0, so it makes sense that we really want to be sure that if beta equals 0, alpha must also equal 0 as well. Alpha equals 0, beta has to equal 0. And this is the new time step restriction I was talking about earlier. Before, we have to delta t must be less than delta t forward Euler, but since we're doing delta t times beta over alpha, that means beta over alpha delta t must be less than the forward Euler time step restriction. Makes sense, right? So now we're going to rewrite this, and we're going to say, well, since beta over alpha delta t must be less than delta t forward Euler, then we can rewrite that as delta t must be less than this coefficient c, which is really your alpha over beta times delta t forward Euler. So your new time step restriction that we're going to be looking at here actually just has to be less than some constant times what forward Euler has to be under. And we'll call this C value your positivity preserving coefficient. Since this is a restriction on your step size, we want to have the largest positivity preserving coefficient possible, so we have more freedom in your time step. One easy way to do this is, well, if we allow more freedom in our stages and increase the number of stages in your Runge-Kutta method, then your coefficients can be a little larger. But if we're really trying to look at efficiency here, because we're looking at time stepping, we have to look at how many functions evaluations we take. So we're going to actually look at this thing we call C effective, your effective positivity preserving coefficient, which is your coefficient divided by the number of function evaluations, or C divided by X, which is the number of stages. So this is really, I'm just going to give examples of how this really works out. So this is the second order two-stage positivity preserving Runge-Kutta method. As you see, the first step is just really just a forward Euler step. And then if you look, your alpha is 1/2 and your beta is 1/2. So if you actually factor to 1/2, you really see it's just U plus delta T F of U. So in each time, the ratio between your alpha and beta is 1. So we actually have for the second order method this positivity preservation coefficient of 1. So we actually don't have to modify our time step. But if you actually think about it, since it's 2 stages, we actually took 2 function evaluations. So if we're looking for efficiency here, our C effective is actually 1/2. Although it's half the size of our time step, we're actually reaching to a whole other higher order of error decay. So instead of your order going down delta t to the first, delta t to the second. So I think it's worth the payoff. And to really drive this home, we'll show what a 3-stage Runge-Kutta method looks like. It's the same idea. So here we have 1/4, 1/4. So C equals 1, C equals 1, C equals 1. If you ever have a case where you have different values at your stages, we always have to look at the minimum C value given to us because we want to ensure positivity in every stage. We need a constant time step. So just be clear about that. So since we have C equals 1, that means your effective is C effective equals 1/3. So now we drop down to 1/3 or 0.33, but you get the third order method. It would be nice if we could always do an S-stage method. So if P equals S, number of stages, get the same order. That's not really the case for positivity preserving. If you actually want to get to a 4th order positivity preserving Runge-Kutta method, you actually have to bump it up to 5 stages. And that was found by Ruth and Spiteri. Sorry if I said that wrong. And if you actually do a 5-stage 4th order method, we get a C equal to 1.5 or a C effective of 0.3. So if you compare the 3rd order method, which is you get a C effective of 0.33, you drop down to 0.3, but you get a whole other order of decay, which is really nice. So this method's higher order, and it's not much more costly. And if that's too restrictive on you, you can really just keep adding more stages, and then do a 10-stage 4th order method, then you get S equals 6 or C effective of 0.6. So it's twice double the efficiency, I guess, and so you get fourth order. It's really up to the user. And make sure you have a whole table, look at your number of stages and look at the order you get. So if you want to actually do 10 stages fourth order, you get a coefficient of 0.6. For second order, the optimal second order positivity preserving methods have a nice form that your optimal coefficient is actually going to be the number of stages, s minus 1 divided by s. So a two-stage second order method is 0.5, so it's 1 over 2, 2 over 3, 3 over 4, and so on. As you can see, as you increase the number of stages, you get like a lot of diminishing returns. So eventually you're going to stop because the payout's not really there. But notice how this second order method roughly approaches 1. That's a really important thing to see. Also notice our table stops at fourth order. And the reason that is because there's no such thing as an explicit positivity preserving Runge-Kutta method that goes higher than fourth order. The best we can get is 4. And that's really kind of rough because now we have a pretty tight order barrier on our positivity preserving Runge-Kutta methods. So something to talk about. As that table suggested, the best C effective we can actually get is 1 for explicit Runge-Kutta methods. Actually, if you want to look at linear multi-step methods too, you can decompose. You can do the same idea, but you're only going to get C effective equal to 1. It's the best you can get. The difference here is Runge-Kutta methods have a positivity preserving barrier of p less than or equal to 4, while multi-step methods don't really have the same idea. So the same barrier. Thing is, their positivity preserving coefficient is a lot smaller. To really point out, if you want to get fifth order multi-step method, you have to take 7 previous solutions to get there, and your C is actually 0.038. That's 0.038 times whatever formula it needs to have for a step size. So that's very restrictive. But we see like a nice little thing in best of both worlds. Multi-step methods don't really have the same order barrier. Okay. Runge-Kutta methods really have more effective coefficients. So maybe there's a way we can combine them together. So really quick, this is how you would actually write a multi-step Runge-Kutta method. Here we have these D's on your previous solutions, out A hats on your function evaluation previous solutions, and this is really your Runge-Kutta method right there. An easier way to look at that, for me at least, is we just have a bunch of matrices full of coefficients, D times your old solutions, delta T A hat F of U, and then delta T A times F of Y. F of Y are your stages. So that's how you can construct your stages of your Runge-Kutta method, and that's how you actually go to 4 1 step in time. Alright, so some cool thing about this is explicit multi-step Runge-Kutta methods, since multi-step methods have a C effective barrier of 1, and Runge-Kutta methods have a C effective barrier of 1, then it makes sense that when you combine them together, you're still going to have the same barrier. The way we're actually looking into this problem is, instead of just doing it by hand, we actually formulated this whole idea of what's the best positivity preserving coefficient we can get of a certain order with a given number of stages and steps. And our goal is what's the best we can do it. So in order to do this, we used optimization software. We used FMinCon and MATLAB, more particularly SQP is the type of optimizer we use. And my goal was to find the best methods out there. Here's an example. Before, when I said second order Runge-Kutta methods actually got a positivity coefficient max at s minus 1 over s. Well, if you actually had one previous time step, look, we actually get the square root of that. The square root of something less than 1 is actually going to be bigger. So see, now we get the square root of 1/2, square root of 2/3, and so on. So we actually get a larger return here. Also, as we increase the number of steps, sometimes you actually get better coefficients. That's not always the case, though. Here, if you look, another major thing to point out is, after doing some more experiments, we noticed a trend in these optimal methods out there. And from that, I was able to mess around with the order conditions, and we were able to prove that we generated some explicit formulas for a k-step s-stage method of order 2 to get the optimal coefficient. And we have some formulas that generate a method for you. So third order, I'm just going to show you some different cases. The main thing to point out here is, although I said before in second order, sometimes adding more steps actually helps you get better coefficients, that's not always the case. Even if I increased it up to 6 steps available for the optimizer to use to try to get the best coefficient out there, it kept always